I'm Benji. I'm an astronomer from the University of Melbourne. That man is Dylan Linton. He's a guitarist from the School of Jazz. And together we are Starburst, blend of science and music for your ears and for your brains. Today, I'm going to talk to you about space, how we perceive it, how we quantify it in 5 dimensions, 3 of which are the same. Dylan, give me a Euclidean kite beat. When we usually think about space, we think about it 3-dimensionally. Front, back, left, right, down, and up. Front, back, left, right, down, and up. And in this world, we see space as 3 dimensions. X, front, back, Y, left, right, Z, up, down. And that's the way that people usually learn to count the dimensions of our space in which we live. But it's not the most convenient way to think about space. Because if I'm moving, I don't go left, front, front. That's not how we naturally move. It's a really artificial construction, and it's constricting. Instead, how we classify dimensions is in 2 different ways: direction and distance. So we're going to start with direction. When we decide which place to move, we look around. We find an object that interests us, and we move directly towards it. It's still 2 dimensions. It's 1 to find our target, and 1 to tell us how far or close to go. Now, when we think about space, it gets a bit more complicated, because this time, we've got a lot of directions available to us. And you need 2 numbers to classify it. Our first number we think of is pan. It's left-right. It's longitude. Or in space, we call it right ascension. And right ascension is measured in hours. 1 full circle of right ascension is 24 hours. And we think about it in this way because in one day, there are 24 hours. And if we look at some star in the sky and we wait 1 hour, we see that it's moved 1 hour in right ascension. 2 hours, 3 hours, 4 hours, all the way around, making a full circle of 24 hours. But alone, those 24 hours don't let us point to everything. I can't point over there. I can't point over here. I can't point at that. To get that, we need a second number, a galactic latitude. And we call that declination. 0 at the top, 90 in the middle, 180 at the bottom. Declination is our galactic latitude, and that doesn't change. Depending on where you are at Earth, you are stuck looking at that side of the sky forever. That's why people in the northern hemisphere can see northern constellations like the Great Dipper. And people in Australia, we can see our own set of constellations like the Southern Cross. But with these 2 dimensions, right ascension, declination, we can point to anything that we want. And this is how a telescope moves. You set its right ascension, you set its declination, and then you let it track so that every hour it moves by 1 hour of distance in right ascension. And it's these tools that we use to watch the skies. But this is only the first 2 of our dimensions. Our 3rd dimension, distance, is an exciting one because it ties directly to our 4th dimension, which is time. Time is distance. Distance is time. We stretch time before us and distance unfurls, and the reason for this is that light has a speed Causality itself has a speed. The universe has a speed that it runs at that cannot be broken. And the speed of this is the maximum speed that anything, not just light, but anything can reach. And this speed is 30 centimeters per nanosecond. When I look at Dylan, I see him as he was 3 nanoseconds in the past. And Dylan sees me as I was 3 nanoseconds in the past. But neither of us is before or after the other one. It's just a matter of perspective. It's relativity. Both of us live in each other's past, but that is because the now is curved. It's not flat. We don't have the same now for all people. Every single point, each one of us has its own now associated with it. And when we look back into people that are a distance from us, we see that their nows are not our nows. They are in the past. If I look further away towards that pole, I would see it not 3, but 10 nanoseconds in the past. And as we look out to further and further distances, things take longer and longer for their signals to interact with ours. If I were looking at the moon, it would take about 1 second, and our nows would differ by 1 second. I would be 1 second behind the moon, and the moon would be 1 second behind me. When I go to the sun, that number grows larger to 8 minutes. We are 8 minutes in each other's pasts. And it gets stranger still at Pluto. Now there's a much greater distance between us, and we are 4.5 hours in the past from each other. 8 a.m. on Pluto is 4 a.m. here, and 4 a.m. in Pluto is 12 p.m. there. It doesn't make a lot of sense, but we keep going. We look further, and as we look further, the light takes longer and longer to reach us. We span across space until after 4.2 years, our light reaches Proxima Centauri, our closest star. And if we let this light travel for not decades, not centuries, but millennia, after 26,000 years, this light would have reached the center of our galaxy. Which means, by the same side of the coin, the light from our center of galaxy has taken 26,000 years to reach us. But it doesn't end there. If we wanted to go to a closer galaxy, there's some that we can actually see from our declination with the right ascension. You can look out, and on a clear night, you might see the large Magellanic Cloud looking like a thumbprint. In places with low light and pollution, it's visible. But that thumbprint, that's one of our close galaxies that is orbiting around us. And the light from that galaxy has taken 150,000 years to reach us. But of course, this is just the beginning of what we see in the universe and the great distances that are involved. But to get to there, I'd like to take you via a different dimension that we think about. One that may not appear as much of a dimension as the other ones have so far, but one that I consider to be of fundamental importance to observing the universe. And that dimension is color. And when we think about the colors that we see, we classify them in 3 ways: blue, green, and red. 3 different wavelengths of color that come together in harmony to make the vision that we see before us. Blue, green, red. And each of these notes, colors like notes on a scale, are separated from each other, with blue being the highest frequency top note, green being the middle frequency middle note, and red being the bass. 3 notes making up this scale of colors that we see before us, and by different combinations of the high notes, the low notes, and the middle of the notes, we see everything that we see. But that's not everything that there is. And when we look at the universe in different colors, different features are revealed to us. So when we go redder than red, we go to longer than long wavelengths, and we see the universe as it is in infrared. And from this, it's not the stars and their bright colors that excite us, it is the gas between them. These absorption features, these thermal emissions that are bonded to us more strongly. When we look even further than than blue and go to higher and higher frequencies and more exciting wavelengths. We could look at the universe in ultraviolet and see the stars bursting, these young stars that overpower us with UV radiation much stronger than the sun. Or we could go even higher to that, to the realm of X-rays, extremely excited energy sources, or gamma rays produced by the brightest of supernovae. A whole spectrum of colors in the universe awaits us, and with different telescopes we see the universe not just in one color, not just limited to the field of human vision, but extending beyond in both directions to observe the universe as far as we can. And when we think about the universe in color, we can notice one thing, that is, that the universe is expanding. And as it expands, light that was originally at long wavelengths expands to longer wavelengths. Things that were blue shift, they become green. Things that were green shift, they become red. Things that were red shift and become infrared, all the way down. So the universe that we observe as it expands gets redder and redder. Its color changes. But what powers this expansion, this dark energy that flows between galaxies? Nobody knows, science is yet to answer. But what we do know is how it affects the things that we see. If we look at things as they were, not light years in the past, but light millennia in the past, light from millions of years ago, light from billions of years ago, when the universe was still young, when stars and galaxies are still in their infancy, when stars hadn't even been born yet, back to the very birth sites of the universe, we see as it was redder and redder and redder until it's not visible at all. And that lies the limit of our view of the universe as we see it today. Because the further back in time we go, the redder things get. But this is beautiful, because what this means is we can look at a galaxy and just from its color, just from how red it looks to us, we can know exactly how far away to find it. And if we know how far away to find it, then we can know when it existed and what point in the universe's evolution this points to. So the color of galaxies gives us this fossil record that lets us delve back in time and see the universe with its different galaxies in different stages of creation. It's like archaeology, but rather with depth being accomplished at time, it's color. And so we build our telescopes, and we build them redder and redder, so we can look further and further back in time to see clues on our universe as it was in the past, further and further back, trying to get to the dawn of time. Keep going. And when we look back even further, we can see that the dust our universe is just expanding. But if we go back in time, it's contracting, getting smaller and smaller. And as it gets smaller, it gets denser and denser. Things that were billions of kilometers apart become so close that you couldn't even see it. And that is the beginning of our universe as we see it. A thick smoke that we can't push through, with its light stretched from its white hot to be longer and longer and longer until it is just a background of microwave radiation, all permeating, surrounding us, invisible to our eyes, but visible to our machines, our mechanical senses that enhance our vision beyond the normal. This cosmic microwave background is the first picture that we have of our universe. Baby photo and ultrasound showing not galaxies, but tiny quantum overdensities that represent places where these galaxies will not yet to be born. Ladies and gentlemen, please welcome Tangled Orbits.